Introduction to multihazards. First, I'd like to introduce the Meteor project, which enabled the creation of this video. Meteor stands for Modelling Exposure Through Earth Observation Routines and was funded by the UK Space Agency through their International Partnership Programme as part of the Global Challenges Research Fund. The Meteor project aims to develop innovative application of Earth observation technologies to improve understanding of exposure. Natural hazards have had escalating impacts, which are contributed to by an increasing exposure of population and assets. However, a major challenge when making disaster risk management decisions can be a poor understanding of the distribution and character of exposure. Robust quantitative methods are required to justify these decisions, and in this project, we are looking at the use of Earth observation technologies within that context. Within the Meteor project, there is also the aim to share knowledge. This video is produced as a part of a series of educational videos to enable the use of Meteor products and data. In this introduction to multihazards, I am going to cover what are multihazards, the importance of understanding multihazards, the different types and scales of multihazards, methods for modelling multihazards, and a few different ways of visualizing multihazards. So let's get started. What is a multihazard? Before we consider what a multihazard is, it's important that we define a single hazard process. The United Nations Office for Disaster Risk Reduction, or UNDRR, states that a hazard is a process, phenomenon, or human activity that may cause loss of life, injury, or other health impacts, property damage, social and economic disruption, or environmental degradation. There are many models that have been developed to assess single hazards. These models vary, but fundamentally they make an attempt to quantify the nature, intensity, and return period of specific hazards. Multi-hazards, however, are firstly the selection of multiple major hazards that a country faces, and secondly, the specific context where hazardous events may occur simultaneously, cascadingly, or cumulatively over time, taking into account the potential interrelated effects. The importance of multi-hazards has long been recognised. In 1992, the United Nations Environment Programme stated that pre-disaster planning should form an integral part of human settlement planning, and that it should include the undertaking of complete multi-hazard research into risk and vulnerability of human settlements and settlement infrastructure, including water and sewage, communication and transportation networks, as one type of risk reduction may increase vulnerability to another. For example, an earthquake-resistant house made of wood will be more vulnerable to windstorms. Furthermore, the 2015 Sendai Framework for Disaster Risk Reduction recognises that disaster risk reduction practices need to be multi-hazard and multi-sectoral, inclusive and accessible in order to be efficient and effective. In practice, assessing multi-hazard interactions is complicated. Each single hazard exhibits its own characteristics, such as time of onset, duration, and extent, and because of this, multi-hazard assessments have to be able to address that hazards may be related to each other and potentially cumulative, something we refer to as hazard cascade. That the impacts on elements at risk, such as buildings or infrastructure, can be different for differing hazards and occasionally may be opposing. The differences between the hazard's characteristics and therefore the methods used to observe and monitor them, and that any of the existing measures of hazard quantification needs to be adapted to allow for comparison of multiple hazards. Not all multi-hazards are related to each other or to an area in the same way. These interactions can vary both spatially and temporally. The most comprehensive classification of these types of multi-hazards is a recent scheme defined by Tilloy et al. In this work, the authors define 5 different hazard interrelations that demonstrate how hazards may be related to and affect each other. The first of these types are independent hazards. Independent hazards are hazards whose causes are independent of each other, but that have a spatial and/or temporal coincidence. This may be, for example, the arrival of a tropical cyclone occurring simultaneously with a volcanic eruption. This was famously the case during the large eruption of Pinatubo volcano in the Philippines in 1991, when Typhoon Diding made landfall as the paroxysmal phase of the eruption began. This category of hazards can also take into account hazards that occur in the same place but at different times. For example, if a cyclone were to hit an area that had recently been impacted by an earthquake. The second type of relationship defined in this scheme are triggering or cascading hazards. In this case, there is an implication of a primary hazard that causes the onset of one or more secondary hazards. This secondary hazard may be identical to or entirely different from the first. So, for example, we may see an earthquake trigger a landslide, as occurred in Nepal in the 2015 Gorkha earthquake event. If an earthquake were to trigger a landslide, which then blocked a river and caused a flood, then this would be referred to as a hazard cascade. The next type of hazards are those that create change conditions. By this we mean that the incidence of one hazard changes the probability of a further hazard occurring due to a change in background conditions. This may be environmental conditions. For example, when a wildfire causes areas of vegetation to become denuded and harden the underlying soil, this can amplify the strength of following floods due to decreased infiltration and increased ground flow. This exact set of conditions in New Mexico in 2011 led to severe flooding a month after a large wildfire. Compound hazards represent cases where the same primary event or large-scale process can cause different hazards to occur. These hazards occur simultaneously and are therefore not considered to be primary or secondary. For example, the co-occurrence of river flooding and sea surge that both result from the same cyclone event. This could be considered as a compound event. The final type of hazard interaction is mutual exclusion. In this case, we consider that two hazards have a negative dependency and therefore do not occur at the same time. This may be something such as heavy rain and fire. It is important to consider these interrelationships and the scales over which they occur, because it will have implications for how this multi-hazard information can be used. If a hazard is only related to another hazard spatially, for example, then we can assume that the hazards have different sources and therefore occur at different times, even if they affect the same area. The spatial relationship of hazards may have implications for mitigation methods such as building codes and building design. It is possible that if these are not properly considered, then the efforts made to stabilize a building from one hazard may destabilize it in reference to another. If a hazard is neither spatially nor temporally related to another event, then we assume that these must be different hazards, occurring in different locations at different times. This, of course, means that there is no relationship that may affect the physical vulnerability of buildings and/or infrastructure because of these hazards interacting. However, it may be important to consider the implications of this when considering public awareness and education campaigns at a national scale, so that populations can be informed of the hazards most relevant to them and their everyday lives. Hazards that are related spatially and temporally occur at the same location at the same time, potentially acting as triggering or compound hazards. This is important for understanding the implications of hazard cascades or indeed the simultaneous impact of hazards on buildings, response and pre-positioning planning. An area defined in a single hazard assessment scenario may be defined as low hazard, but when a multi-hazard aggregation is taken into account, it may be that this location is more exposed to multiple events occurring at the same time, exacerbated by each other. Finally, if hazards are only related temporally to each other, then we can assume that they are occurring at the same time but in different locations. This will have implications for emergency planners who may want to consider preparing for scenarios where they are called upon to manage two events from separate administrative units simultaneously, splitting resources and personnel. Multi-hazard models can aim to address some or all of these interrelationships and scales, depending on the availability of underlying data and the purpose of the model. The function of a multi-hazards model is at the most basic level to develop a structured approach to aggregating two or more single hazard assessments so that they can be compared and potentially integrated with vulnerability and exposure data. The principal difficulty in the comparison of multiple hazards is that each hazard will have a distinct reference unit. Before any types of modelling can be employed, it is necessary to perform some sort of standardization of the data to a common measure. There are two main ways to do this that give rise to two different types of modelling. These are classification of hazards and development of indices. Depending on how these standardization calculations are approached, a model can be thought to be qualitative, semi-quantitative, or quantitative. The classification of hazard is the most frequently used approach when standardizing between hazards. Intensity and frequency thresholds are defined in order to classify the representative hazards into a predefined number of hazard classes, for example, high, medium, and low. This allows for an equivalency between hazards, as a high hazard earthquake would be in line with a high hazard flood, for example. Classification creates compatibility between the hazard and vulnerability classes, but also results in equivalence of all the single hazard classes, which may not reflect the frequency distribution of these hazards. Classification methods can therefore be thought of as qualitative methods. The table on the right of this slide is an example of a hazard classification scheme that was developed as part of the European Armonia project. This simple scheme classifies the hazards as high, medium, or low based on their intensity. Comparatively to the classification method, the development of indices allows for a continuous standardization of differing and therefore not directly comparable parameters. This is often achieved by developing indices that can then be uniquely weighted to reflect the more likely impact of the hazard and vulnerability class. In their study that aims to identify areas in the Eastern Mediterranean where population are likely to be exposed to several hazards at the same time, Al-Mojani et al. Separately model a number of hazards which they then classify using separately defined thresholds. They then apply a weighting factor that accounts for the expected impact on humans and the economy. Once they have summed these weighted indices, they are able to produce the multi-hazard index distribution map displayed here. Once they have summed these weighted indices, they are able to produce the multi-hazard index distribution map displayed here, defining 5 intensity levels of multi-hazards. The use of weighted indices in this study allows the authors to develop a semi-quantitative model which accounts for the different impacts of differing hazards. Quantitative methods result in the calculation of absolute values on a determined scale. These therefore provide the most statistically robust information on potential damage or losses and are therefore predominantly developed by the reinsurance industry. The complexities I have touched on in the previous slides have led to the development of many methodologies for assessing multi-hazards. It is perhaps not surprising that these methods can vary a lot from each other. There are several very useful and detailed reviews available that outline the current state of the art, the references for which can be found at the end of this talk. Generally speaking, however, the variations of models fall into the following categories. The type of hazard. Some studies only address natural hazards, whereas others include anthropogenic hazards, such as chemical spills or artificial hydrological changes, drainage and dewatering, for example. The scale of the model can vary greatly depending on the aims of the assessment. It may address an area as small as a city or catchment area, or it may be designed to capture multi-hazards at a regional, national, continental, or even global scale. Generally, those models that are designed for use at finer scale require a larger amount of input information than the models that have been designed for use over wider areas. Depending on the focus of the study, the model may require very different skill sets to collect the required input data. For example, a study that focuses heavily on gathering detailed building information may require civil engineers to perform building surveys. A study requiring a focus on socioeconomic parameters, however, will necessitate the inclusion of social scientists and economists during the data collection phase. As I mentioned earlier, the way in which a model standardizes hazard data, be it fully qualitative or fully quantitative, is one of the key differences between the construction of the various available multi-hazard models. A fully quantitative approach usually requires that the user include probabilities calculated from well-characterized frequency-magnitude relationships and complete inventories of economic, social, and cultural impacts from previous events. As you can appreciate, for quantitative models, we generally require a denser data set with well-established uncertainties. Semi-quantitative and qualitative models can be useful in cases where we don't have access to this type of information. For inputs, models may include only hazard information or may incorporate hazard and vulnerability data. For example, the Disaster Risk Index by Peduzzi et al., which includes hazard assessments as well as an assessment of 32 socioeconomic indicators. Finally, an important variation is the type of end user that the model is aimed at. Models can be designed to provide information to local authorities, urban planners, engineers, building owners, civil protection services, insurance companies, or the public. This makes a difference in how they are constructed and what input parameters are included. When designing a model for assessing multi-hazards, it is important to consider variables such as these so that the final product is fit for purpose, but also does not overinterpret the data available, allowing for uncertainties to be captured where possible. In the next presentation, I will cover how we have developed a multi-hazard model to incorporate the single hazard and exposure assessments that have been generated as part of the Meteor project. As well as making sure that you consider the interrelationships between the hazards in your study, the scales that they occupy, and the different methods and variations of modelling, it is necessary to consider how you may visualise the outputs of these models. A single hazard visualization refers to a set of maps that displays the single hazards one by one. This is beneficial if you would like to observe and interpret the patterns for each process in detail. However, they are perhaps less useful than other methods as they keep data separated. One way to mitigate this is to arrange images next to each other so that attributes can be compared over several outputs. In the figure here, we can see how this approach was used by Bartle and Muller in their risk analysis of the Horn of Africa. In this study, they separate out the different hazards such as flood, drought, earthquake, and locust, and then display sets of maps from each one, projecting the hazard, exposure, and risk separately. Single hazard visualizations are often a first step towards understanding multi-hazards, and are followed by a presentation of merged or joint variables. Visualizing joint variables can be done in several different ways. Variables can be summed, multiplied, or counted, thus reducing the multidimensionality of one parameter. They can also be displayed as a number of relevant processes per pixel, as is shown in the simple representation from the World Bank's Natural Disaster Hotspots Global Risk Analysis, which displays a multi-hazard index that reflects the number of hazards considered relatively significant in a particular grid cell. It is also possible to display information such as the annual occurrence probability of the hazards addressed within a study. In the study by Bartle and Muller, they aggregate the single hazard visualizations from the previous slide to generate a hazard annual probability and most probable hazard output. In contrast, maps that visualize multiple hazards or risk at once provide simultaneous information about hazard patterns and the spatial coincidence of these. This can make figures busy and difficult to read, especially where hazards overlap. One way around this is to use an approach that divides hazards into type classes. This example from the 2009 Global Assessment Report, or GAR, divides hazards into weather-related and tectonic hazards. This is just one of many approaches that have been taken by different authors. If you are interested in a summary of these methods, then the review paper by Capps et al. Provides a great overview and also touches on digital GIS-based maps that have the potential to be flexible visualizations. The topic of multi-hazards has many different components, and this talk is designed to be a brief introduction only to highlight some of the parameters to keep in mind when exploring multi-hazard modelling. In summary, there are different types of hazard interrelations and scales of hazards. The comparison of hazards is difficult due to different process characteristics. Classification and index schemes can help to overcome this problem. There are many existing multi-hazard models that have been designed to address differing variables. It is therefore important to assess these parameters before applying or designing a model. Visualizing multi-hazards is non-trivial and may require different outputs for different end users or purposes. This is the end of this introductory talk on multi-hazards. Further information on all the concepts discussed here can be found in these key references, which were used in the construction of this talk. The 2 review articles that I mentioned earlier are in bold font. In the next talk, I will elaborate on how we have addressed multi-hazards in the Meteor project and show some initial results from our national models.